Welcome everyone to this explainer. I am so incredibly excited today because we're looking at a piece of everyday tech that is literally vanishing into thin air right before our eyes. I mean, we rely on it every single day to stay connected, yet it's undergoing this radical transformation from a physical object you can hold in your hand to, well, pure invisible software. I'm talking, of course, about the SIM card.
Okay, let's dive into this. Have you upgraded your smartphone recently? If you picked up an iPhone 14 or one of the newer models in certain markets, you probably noticed something completely missing. The physical SIM tray is just gone. No more tiny little hole to poke a paperclip into. The plastic chip we've spent decades swapping between phones has just disappeared from the design entirely. But to really grasp why this shift towards eSIM technology is such a massive deal, we first need to look at the sheer scale of the physical SIM cards we've been dealing with.
Consider this staggering number, 4.5 billion. According to industry research, 4.5 billion physical SIM cards are issued and shipped around the world every single year. That is an almost incomprehensible volume of physical objects being manufactured for, honestly, temporary use. I mean, every time someone changes a mobile network or buys a local data plan while traveling, another one of these little chips is handed over, used briefly, and then usually just thrown in a drawer or discarded.
And here is the real cost of that staggering volume. Those 4.5 billion cards? They create 18,000 tons of plastic waste annually, mostly PVC and other polymers. And to put that into perspective, the global logistics of shipping these tiny cards all over the planet generates about 560,000 tons of CO2 emissions every single year. So this sets up the real environmental stakes for our explainer today. We're not just talking about a neat little tech upgrade, we're talking about eliminating a massive global source of electronic and plastic waste.
So here's our roadmap for today. We'll start off with the Shrinking Act, then move to the secret handshake, and look closely at the eSIM shift. After that, we'll cover remote provisioning, examine the security risks, and finally look ahead to the iSIM future.
Let's start with Section 1, the Shrinking Act. I promise this is going to blow your mind when you see just how drastically this technology has dematerialized over the decades. To really appreciate where we are now, let's trace this timeline. Back in 1983, the first mobile phone, the Motorola Dynatac, didn't even use a SIM card. It weighed a whole kilogram and cost $4,000. When the first actual SIM card launched in 1991 for the GSM network, it was literally the size of a standard credit card. Can you imagine? Over the years, as space inside phones became premium real estate, the SIM just kept shrinking. We went down to the mini SIM in '96, the micro SIM in 2010 with the iPhone 4, the Nano SIM in 2012, and finally, the first commercial eSIM in a smartwatch back in 2016. It's this incredible evolution of just carving away plastic until there was literally nothing left.
Which brings us to Section 2, the secret handshake.
Now what's really interesting here is moving beyond the physical plastic to what a SIM actually does inside your phone. At its core, a SIM, which stands for Subscriber Identity Module, is basically a tiny, highly secure circuit board. And its main job? Holding the IMSI, the International Mobile Subscriber Identity. Think of the IMSI as your ultimate all-access VIP pass to the cellular network. Alongside this identifier, the SIM securely stores secret cryptographic keys that prove to your mobile network operator that you are exactly who you claim to be.
So here's how that authentication actually plays out in a fraction of a second. When you turn your phone on, it makes an initial connection to a cell tower. The network then asks for your IMSI. But it doesn't just take your word for it. It initiates Step 3, a challenge response mechanism. Basically, the network sends a random mathematical puzzle, a challenge, to your phone. Your SIM card uses its hidden secret key to solve this puzzle and sends the response back. The network does the exact same math on its end, and if the two answers match, boom, you're verified and your call goes through. And the best part? That secret key never leaves the SIM card, which is exactly what makes it so incredibly secure.
Let's move on to Section 3, the eSIM shift.
And this brings us to the core focus of our explainer today. We're moving away from the physical card completely towards an embedded SIM that is permanently soldered into the device's motherboard right at the factory. The contrast here is just stark. The traditional SIM requires constant virgin plastic production, it requires mining for silicon and gold, plus that massive global air transport network we talked about earlier. But the eSIM reality? No new plastic, no new mining for removable chips, and literally zero shipping emissions because the profile is downloaded purely as software. It's an absolutely massive win for sustainability.
And going green definitely doesn't mean sacrificing convenience. Actually, it enhances it. The shift to eSIM offers huge consumer benefits. For instance, devices like the iPhone 14 can store up to 8 different eSIM profiles simultaneously. Think about traveling internationally. Instead of hunting down some random local kiosk at the airport and fumbling with a tiny paper clip to swap out a piece of plastic, you literally just download a local data plan through an app and you're instantly connected. It is seamless, it's flexible, and it's 100% digital.
Section 4. Remote SIM Provisioning. So, this begs the question, if the SIM is permanently soldered into the phone at the factory, how does your specific, highly secure network profile actually get onto it? The answer is Remote SIM Provisioning, or RSP. This is a standard created by the GSMA, the Global Organization for Mobile Operators. RSP is essentially the software magic that completely replaces physically swapping a card. It allows a digital SIM profile, including that top-secret key we talked about earlier, to be securely downloaded over the air, right into the phone's secure hardware element.
Let's walk through exactly how this digital delivery flows. First, you buy a plan, and the mobile network orders a profile. Second, a highly secure server, known as an SMDP Plus server, prepares your specific profile. Third, a piece of software on your phone called the Local Profile Assistant, or LPA, reaches out to that server. And finally, the profile is securely downloaded and installed directly into the EUIC, which is that embedded hardware chip in your phone. The whole shebang happens in seconds, entirely over the internet.
Now for Section 5, Security Risks.
While digitizing our mobile identities is incredibly convenient and obviously great for the environment, it does introduce a whole new landscape of vulnerabilities. A formal security analysis by researchers at Aalto University rigorously modeled this GSMA protocol, and what they found was that while the system works perfectly when everyone is honest, in realistic partial compromise scenarios, like where participants make mistakes or humans get tricked, the digital system really begins to show significant cracks.
So the crucial point is understanding these specific vulnerabilities. The researchers pointed out that the protocol relies heavily on being encapsulated in a TLS internet tunnel for security, which is an unnecessary weakness. But more alarmingly, there's a lack of pre-established identifiers. This means if a download server anywhere in the world gets compromised, it could theoretically be used to attack honest users. Plus, because it's so easy to just scan a QR code to download a profile, there's a severe lack of reliable methods to verify true user intent. Just as someone could physically steal a SIM card in the past, a malicious actor who gets a hold of your activation code could hijack your digital profile before you even install it. We've basically traded physical security risks for digital ones.
Finally, Section 6, the iSIM future. Let's see how this builds into the ultimate evolution of this tech.
If the eSIM was all about soldering a chip to the motherboard, the iSIM takes it one step further. The iSIM, or integrated SIM, eliminates the dedicated SIM chip entirely. Instead, it bakes the SIM's highly secure operating system directly into the device's main processor, the system on a chip. So think about that. The SIM card went from a credit card-sized piece of plastic to a standalone microchip, and now it's just a secure block of code running inside the main brain of the device.
And why does this matter? Well, by removing the separate hardware, manufacturers save crucial millimeters of space and drastically lower energy consumption. This is an absolute game changer for the Internet of Things. Think about tiny devices where space and battery life are everything. Smartwatches, medical sensors, or, tiny pet trackers. The iSIM allows these tiny devices to connect to global cellular networks without needing the space or the power required by traditional or even embedded SIMs.
Which brings us to our final thought for this explainer. We are rapidly moving toward a zero-waste, instantly connected world where our digital identities can be downloaded anywhere on Earth in a matter of seconds. But as this physical technology vanishes into pure software, we really have to ask, is this ultimate convenience worth the complex new security risks required to protect our invisible identities? It's a fascinating trade-off, and definitely one we'll all be navigating as our devices continue to evolve. Thank you so much for joining me on this deep dive. Keep asking questions, and I'll catch you in the next explainer.